So find the interval of convergence. For the following series or power series. Okay. So this one is summation x to the 2n, 4 to the n, and starting from 0 to infinity. So this is basically a sum of, you can call it a sub n. I don't know how we call it, a b sub n, it doesn't matter. And from 0 to infinity. So we use ratio test, and we said we are finding x's such that a sub n plus 1 over a sub n, this limit, absolute value, is less than 1. So something I want to mention here is that you can do the same with a root test. So if you can find all x's, so here I add or nth root of absolute value of a sub n, if that limit is, if you set it less than equal 1 strictly and find all those x's, that's also true. Okay, so you can use both, whatever is easier. So as you can see, even root test for this one is even easier, but let's just go with the ratio test. So a sub n plus 1 over a sub n equals to, you have to do absolute value, but it's positive already, so it's going to be okay. So you have to replace n with n plus 1. Right? And reciprocate the other one. 2 to the 2n, or x to the 2n, sorry. Is that correct? Is the substitution correct or no? Like in the first fraction, replacing n with n plus 1. Is it done correctly? What's wrong with it, Donovan? He's right. It's not. It's not correct. It's wrong. What's wrong with it? Yes. Okay. So that indeed becomes x to the 2n plus 2, x to the 2n down here, 4 to the n, and then 4 raised to the n plus 1. And as you can see, it simplifies to x to the second, because x to the 2n cancels. And down here you have 4. Okay? By the way, everything in absolute value. And indeed, you see this has nothing to do with n, right? Independent of n. This is independent of n. So the limit of that is itself. So limit of this ratio is indeed absolute value of x squared over 4 and approaching infinity. Now this has to be strictly less than 1. Okay? And solve for x. Find that range of x satisfying this inequality. So we get x squared is strictly less than 4. Take absolute value, so we get square root. When you take square root, remember, square root of x squared is not x, it's absolute value of x. So absolute value of x is strictly less than 2. That means x is bounded by 2 and negative 2. Okay? So, any questions so far? Now, the extra piece I'm going to do here, so remember, so far, the interval of convergence is -2 to 2. That means for sure we know numbers between those two exclusive make that series converging. Of course, outside diverges, okay? So the only 2 points that is left to check are these 2 points. So we just wonder, do we have to include the endpoints into this interval of convergence or no, okay? And there's only one way to do it. You literally, so let x being 2 and x being -2 and see if the power series with this x value converges or not, okay? So if x equals 2, let's go to the original series, is this guy. So if you let 2 in that, you get 2 to the 2n, 4 to the n, and starting from 0 to infinity. And as you can see, this is, let me write down this step, is 4 to the n, 4 to the n. That's basically sum of 1, and from 0 to infinity. Now question, does this diverge or converge? I'll write the other one. The other one is, also 4 to the n. Okay, so both the same. But the question is, do they converge or do they diverge? The summation of 1 and from 0 to infinity, it diverges, right? Because, well, in this series, let me write Bn. So here, Bn is 1, of course not 0, so by nth term test diverges. So that x to the 2n over 4n only converges for x's in this interval, -2 and 2, exclusive at the endpoint, or open interval, okay? In fact, for these values, let me rewrite that series. I want to go ahead and write the series in this form. It's basically x squared over 4 raised to the n, and starting from 0 to infinity. Question, what kind of series is that? If you start writing down terms, the first one is 1. The next one is x squared over 4. The one after that is x to the 4th over 16. The one after that is x to the 6th over 64. Yeah, that's geometric. So it is, someone could have argued this, geometric is converges only if the ratio, which is, x to the 4th, is strictly less than 1. You could have gotten the same argument. Okay. Let's do another one. Question on this one, by the way. Let's do number. Let's do 2 part B. It's x to the n over cube root of n, and starting from, why is it 2 to infinity? It doesn't matter. 2 to infinity. Remember, guys, we don't even care about what number it starts with, okay? So the behavior of this series would be the same if n started from 20. Doesn't matter. Because you're only, talking about finite number of terms, which is a finite sum. All right. So here, let's name it b sub n. B sub n is x to the n over cube root of n. We do the same thing. B to the n plus 1 over b sub n, absolute value, is x to the n plus 1 cube root of n plus 1 times reciprocate cube root of n x to the n. This simplifies to, as you can see, only one x is left. Cube root of n is already positive, so I put them together and I write it as cube root of n over n plus 1. And I want to emphasize that this 3 is the third root. Should be. It's right there. N plus 1. Any question on this piece of algebra? All right, now let's take limit of that. As n approaching infinity is the x is constant with respect to n, limit of cube root of n over n plus 1, and starting from n to n approaching infinity. Question, what's that limit? The value of that limit is ignore cube root. What's limit of n over n plus 1 as n approaches infinity? It's 1. Now what's cube root of 1? It's 1 again. So that's 1 times absolute value of x is absolute value of x. Now this has to be strictly less than 1. That means x should be between 1 and negative 1. Okay. So the interval we have is negative 1 and 1. Now we just have to check the endpoints. Well, if x equals 1, put it in the series, and as you can see, the series becomes 1 over cube root of n, and from 2 to infinity. Okay, let me write it as 1 over n raised to the 1/3, and from 2 to infinity. Converges, diverges, and why? That's a p series with p equal 1/3. 1/3 is less than 1, therefore diverges. Okay, p equal 1/3, less than 1, diverges. That means we cannot include 1 into this interval. We cannot add the endpoint 1 into the interval of convergence. Okay, so that side stays the same. Now let's check the other side. If x equals minus 1. As you can see, this time series becomes negative 1 to the n over cube root of n, and from 2 to infinity. Now, how about this one? Does this converge or diverge, and why? That's an alternating series, right? The limit of the nth term of the series goes to 0. So by alternating series, this one converges. So by alternating series test, since 1 over cube root of n approaches 0, this guy converges. Therefore, we have to include negative 1 into this. So for this side, we have to go ahead and include it. Negative 1 and 1. So closed negative 1, open 1 interval is the interval of convergence. Oops. Question on that? So now I should be able to do all problems in 10.7. Okay. All right. How did that one go to 0? Okay, can you go over simplification? Let's start with Donovan. Which one do you mean, Donovan? You can open your mic. Of an plus 1 over a sub n. You talk about here? Or up there? Or here? Let me answer Reno's question quickly. How did that one go to 0? Which one you talking about? You talking about this one, Reno? Well, you take the limit of this 1 over n raised to 1/3 as n approaches infinity. Isn't it 1 over a large number? The denominator keeps getting larger, so the whole ratio keeps getting smaller and smaller. It eventually goes to 0. Okay, Donovan, to be honest, I don't know which an plus 1. Do you mean in general, like how to simplify an plus 1 over an in general, or specific problem that we did today? Oh, the last problem. Okay. I assume you're asking about this one. These two together give you the root x, and put these two pieces as one ratio with root, third root. So why didn't x equal 1 go to 0? Okay. First of all, you mean, why didn't this series, your question is, why didn't this series, when x equals 1, didn't convert or doesn't convert? Why does the series doesn't converge when x equal 1? Well, if x equal 1, 1 raised to n is always 1. So the series becomes this guy at x equal 1. But this is a p series, cube root of n is simply n to the 1/3. So that's a p series with p equal 1/3. And we already discussed p series, okay, when p is strictly less than 1, diverges. And this one is not p series. This is an alternating series. The second one. The p series has all terms being positive. This one is not, isolates between positive, negative, positive, negative. That's an alternating series. We had a test where only an, so this is alternating series of this form, -1 to the n over times a sub n. If an alone goes to 0, then the alternating series converges. So it's, your question is, the answer to a question is the difference between these two, right? This one is 1 plus half plus 1/3. This one is 1 minus half plus 1/3 minus 1/4. So if you remember, we showed this one converges, but that one diverges. only because this is an alternating series of the same terms of the left. Okay. Okay. Let me mention something here. Why do we have to do more tests? Because 1 to 0. Okay. I think you're missing the point of alternating series. We had a theorem called alternating series test, which said for an alternating series of this form, -1 to the n a sub n, and from 0 to infinity. If a sub n goes to 0, then series converges. This theorem only works for this type of series. This is not an alternating series. This guy is alternating. Like, we didn't prove the theorem, okay? I did an example. The example I did was this one. So there's a difference between, this one and that one because of only this coefficient, which makes it, the terms being positive, negative, one at a time. Doesn't make sense, Okay. So there's one thing before moving to 10.8 that I want to talk about, and that's it's a simple, operation that we can do to power series. We can derive and integrate power series. Let me do it by example. For example, x to the n over over 2 to the n, and from 0 to infinity, you can take the derivative of this. So I'm just explaining by an example. How? Well, first of all, derivative is derivative respect to x, because remember, this is a function of x. So it's d over dx of summation of x to the n, 2 to the n, and starting from 0 to infinity. Well, you do this term-wise, meaning you can sort of push this inside, okay, and put it right here. So it becomes d over dx of x to the n, 2 to the n, and starting from 0 to infinity. Okay, now just sort of skip or ignore that. If I ask you to find derivative of x to the 7th over 25, what would be the derivative of this? Let me completely put it on one single page. So 125 is a constant, right? So you simply take the derivative of x to the 7th, which is 7x to the 6th over 25, right? So denominator has nothing to do with x. We do the same thing here. This denominator is a constant with respect to x. So simply take the derivative of x to the n, which is n, x to the n minus 1 over 2 to the n. And you still keep taking summation. If you plug n equals 0, remember the original one starts from 0. If you plug 0, you're going to have 0. So for that reason, we started from 1 to infinity. They are the same. Okay. So in general, derivative, I'll illustrate it this way. d over dx of summation of a sub n x to the n and start from 0 to infinity is the summation n a sub n x to the n minus 1 and starting from 1 to infinity. Now if you take the derivative of this again, or d2 dx squared is like second derivative of this guy is, well, you already take the derivative once, take another derivative, so it becomes n minus 1, n times n minus 1 a sub n x to the n minus 2, summation of that, and starting from, so this time you have to start from 2, right? Because 0 makes that one 0, 1 makes that one 0, so the whole thing is 0 for that reason, and starts from 2 to infinity. Okay. You can also integrate. Can also integrate. In general, integral of summation a sub n x to the n and start from 0 to infinity dx. You can write it as summation a sub n integral of x to the n dx, and from 0 to infinity. Okay, which is summation of a sub n. What's that integral? It's power rule, x to the n plus 1 over n plus 1, and from 0 to infinity. So here you keep it from starting from 0 because it doesn't, cause any problem. Okay? And we're going to need it for the next section where we talk about Maclaurin series and Taylor series. So let's do one example. Let's, for example, integrate let's do this one. So integrate x to the 2k over 2k factorial, k from 0 to infinity. Okay. So the integration of this dx, we said we can do it term-wise, okay? So it's a giant thing. You only focus on integrating this guy. What's the integration of x to the 2k dx? We do power rule. It's x to the 2k plus 1 over 2k plus 1. Okay? So this series then becomes summation 1 over 2k factorial times, well, we integrate x to the 2k plus x to the 2k, which is x to the 2k plus 1 over 2k plus 1. K starting from 0 to infinity. Question on that one? Now I'm going to simplify this. We're not done yet. Okay? So let me erase this. Okay. Now if you notice, that's 2k factorial. You multiplying by the next term of that factorial. For example, what is 8 factorial times 9 itself? Sorry. 8 factorial times 9 is nothing but 9 factorial. So for that reason, you can write that summation of x to the 2k plus 1 over 2k plus 1 factorial. K starting from 0 to infinity. Okay. So it's very interesting. This series this one, if you expand the series, write down the first few terms, you'll see it's 1 plus x squared over 2 plus 2 factorial, x to the 4th over 4 factorial plus x to the 6 over 6 factorial, so on. Now, when you integrate this, what does it become? Well, this one is x. I mean, think about it. What's antiderivative of 1 is x. What's antiderivative of x cubed is x. X squared is x cubed over 3. The 3 with that 2 factorial makes it 3 factorial. So we get x cubed over 3 factorial. The next one, integration, is x to the 5th over 5 factorial plus x to the 7th over 7 factorial. So in this sum, you have all the even indices. On integration, you have all the odd indices. And it makes sense, right? When you do integration like that. These two series, they converge to certain functions. You can write them as one single term function. Later, we'll see them in 10.8. Okay. I think you should be fine now for the rest of 10.7. Any questions so far before we start 10.8? I also have some news for you. How many people are there? 7. Ready for the news? I decided. Let me know if you like it or not. Although there are only 7 people here. I decided not to make the final cumulative. In fact, I'm only going to test you guys on series, chapter 10. What do you think? Would you like that idea or you don't like it? Yeah. So only covers chapter 10. That means, you don't have to study. You don't have to go back and study all the integration techniques, work, L'Hopital, surface area, curve length, volume of. Yeah. I mean, I feel like you have to study less. So you don't have to, go over all day. Except these are recent stuff. Okay. So you've been dealing, with this stuff recently. So it makes it easier for you guys to study it. Whereas you might have forgotten. But you haven't been touching with the earlier stuff we talked about. So you like the idea of being tested over series? But remember, the exam is 2 hours long, and you're only being tested on chapter 10. So that means you're going to get a lot of series watching. Just sequence, series, convergency, divergency, absolute convergency if it's conditional, and then power series. Okay, find the interval of convergence, this stuff that we just talked about, and also 10.8. Exam, I can't recall what the date is, so it's going to be same time, same date, no change. If it was initially 22nd, 10:15, 12:15, yes, it is. It's the same. Okay. All right, now let's continue. We have 10 minutes. Let's continue on Taylor series. So Taylor series. Exactly, I start with the theorem. If f of x is differentiable on its domain of any order, I'll explain this by just writing this. Basically, any order derivative of f nth order. Remember, this notation means nth or nth derivative of f exists, okay, and it's continuous. So the nth derivative of f exists. Then f of x can be represented as I have to add something here. That's okay. Let me can erase it. So let's erase that. Then for any point C in domain of f of x can be represented as a power series in this form. F of x can be represented as sigma a sub n x minus c to the n, and starting from 0 to infinity. As you can recall, the c was called the center of the power series, center of convergency, right? And an was the sequences. Well, if you look at this side, first of all, it's very interesting that you can write a function as a summation of infinite terms. Like, think about it. Sine of x is differentiable of any order, right? In fact, the derivatives of sine, there are four, makes it like a loop of four, terms. So the first one is cosine x, negative sine x, negative cosine x, and then sine x. And then this loop goes forever. So it has derivative of any order. Now, by this theorem, sine of x can be written as a summation of infinitely many terms. And these terms are specific terms. In fact, they're powers of x. Like, what the hell? How is that even possible? Right? So sine of x. And by the way, this can be done for any c in the domain. So for any point in the domain of f, domain of sine is literally everything. It's all real values. So for any point in R, for any value in R, you can write sine as a power series, right? So if we can, for example, we can write it as a0 plus a1 x minus for some c plus a2 x minus c squared plus a3 x minus c cubed, and so on. Like, how is that possible? Write sine as an infinite degree polynomial. Like, consider this as a polynomial. Like, this is a polynomial of infinite degree. So it's a very interesting fact. In fact, I don't know if I mentioned this, but this is what they use in computers and calculators to approximate these functions. So when you see e to the second in your calculator, that number is not the exact e to the second. When you see pi in your calculator, when you punch pi in your calculator and you see 3.14, 15, and all those digits, that's not the exact value. That's only an approximation of pi. Now, how is that approximation calculated? By these Taylor series or Maclaurin series, as we call them later. Okay? All right. Let's go back to that theorem. So, f of x can be written as summation of a sub n, x minus c to the n, and starting from 0 to infinity. Well, in this power series, this piece is known, right? It doesn't change. The only thing changes is this guy. Like, what are those guys? So, question, what are a sub n's? Like, how did they relate to f of x? Because every time we change this function, this a sub n has to change, right? So how are they related to f of x? So let me rewrite this question. What relation do f of x and a sub n have? All right. This is the relationship they're going to have. Yeah, it's going to be derivatives. And let me start by an example. Since f of x, I'm going to rewrite this series, but, span it. So it's going to be a0, a sub 1 x minus c plus a sub 2 x minus c squared. And you have infinitely terms, and they all have powers of x minus c, right? The next one is x minus c cubed to the fourth and so on. I want to find this one first. How? Simply let x equal c. If you let x equal c, what happens to all these terms? They all become equal to 0, right? Let x equal c, all those terms except the first one becomes 0. Then there you go. You found the first one. So a sub 0 is nothing but f of c. All right. Let's take the derivative of this. We said f of x is differentiable of any order. If you take the derivative of that, so derive once, we get f prime of x. Derivative of a0 is 0 because it's a constant. Derivative of that is 1, so you get a sub 1. The next one is 2a1 up to a sub 2. 2a sub 2 x minus c to the second 3a cubed x minus c squared. That should be 1. Sorry. But the point is, now if you let x equal c in this one. As you can see, f prime of c equals 0 plus a sub 1 plus bunch of zeros because these all have x minus c in them. So for that reason, f prime of c is a sub 1. So I found that one, I found that guy. We take another derivative, we find a sub 2, okay? Now, let me rewrite the series in this form. F of x equals a sub n, x to the n starting from 0 to infinity. Question. What's the nth derivative of x to the n? Let's start with this example. What is fifth derivative, for example, of x to the fifth. Let's see, the first derivative is 5x to the fourth. The next one is 20x to the cube. In fact, let me write it as 5 times 4, x cubed. The next one is 5, 4, 3, x squared. That's the third derivative. So that's 1, 2, 3. The fourth one is 5, 4, 3, 2, x to the first. All right, now the last one. The last one is 5, 4, 3, 2, 1, and derivative of x is 1. Okay, so what's the fifth derivative? We have a name for that. That's called 5 factorial. Good. So for the same reason, this derivative is nothing but n factorial. Okay. So the nth derivative of this guy is going to be n factorial a sub n x to the, so we take in, let's do it this way. Let's take kth factorial. How about that? So I'm gonna change this to k. Oh, you know what? Let me write it this way. Let me write this as a0 plus. I'm gonna skip all the other terms. Write this term a sub n minus 1 x to the n minus x minus c to the n minus 1 plus a sub n x to the n plus x minus c. The next one is a sub n plus 1 x minus c to the n plus 1. Now when you take derivative of this n times, what's the derivative of all those terms? Well, let me ask you this question. If here, what's the fifth derivative of x to the fourth? That is 0. So fifth derivative of any powers of x less than 5 is 0. So for that reason, nth derivative of all these terms, these ones, where the power is less than n, it's 0. So terms starting from here have non-zero derivative. Derivative of this term, we already showed, is n factorial times a to the n. So from this function, when you take derive at n times, because of the argument we made here, it's n factorial a to the n plus. It's going to be bunch of terms where they have x minus c in them. So it's going to be x minus c. The next one is going to be something x minus c squared plus. And I don't care what these are. We don't even care. What we care is that when we let x equals c, this guy's constant n factorial a to the n plus. What's the value of those guys when x equals c? It's 0. So this is nothing but n factorial a sub n. Now out of this equation, solve for a sub n. All you have to do is divide by n factorial. So a sub n is nth derivative of f evaluated at c divided by n factorial. That was the formula I was trying to prove to you. Thus, f of x has this power series, x minus c to the n. Here, the coefficient initially was a sub n. We figured out what those coefficients are. Those are, as Athena said, it's the derivative, nth derivative of f evaluated as c divided by n factorial, n starting from 0 to infinity. This, ladies and gentlemen, is called Taylor series of function f of x centered at x equals c. We'll do examples tomorrow. So enough for now. Let me stop.